You've never actually seen the real moon. You've only ever seen the same safe face it keeps turned toward Earth, on the hidden far side, inside one of the biggest impact scars in the solar system. China has quietly landed robots where no one has ever walked. And what they've sent back is not just cool pictures, it's the kind of data that makes scientists rewrite textbooks. In this video, you're going to ride along with those missions into a 186-kilometer crater. Dive under the surface with radar that sees hundreds of meters down, and step through a place so extreme, it forces a completely new look at the moon itself, what they actually found there, and why it matters for you standing on Earth right now is what we're about to unpack. You've never actually seen the whole moon, and that's a literal statement. The other half has been hidden from direct view your entire life. That's because of something very simple and very strict: tidal locking. The moon rotates once on its axis in the same time it orbits Earth, about 27 days. One spin per orbit. That keeps the same face turned toward you at all times. So when people say dark side of the moon, it sounds mysterious, but it's actually misleading. The far side is not dark in the sense of no sunlight. It has daytime and nighttime just like the near side. The term dark only means out of sight from Earth. No ground-based telescope on Earth can look over that edge. For most of human history, we literally had no direct data about that hidden hemisphere until spacecraft went round their back and sent images. Here's the key point, and it's very blunt. Every map or globe of the moon you grew up with, every school poster, showed you at the most half of the real object. The familiar patterns of dark patches and bright spots are just one face of a two-faced world. Half the terrain, half the scars, half the history were simply missing from your mental picture. Now you might expect, reasonably, that if you could flip the moon around, the far side would look roughly similar to the side you already know. Same body, same orbit, same general history. But when spacecraft finally imaged the far side, the result was not more of the same. It was a shock. The near side, the side you see, is covered with large dark regions called maria. These are huge plains of solidified lava, basalt, that filled in big impact basins long ago. They look like dark seas. The far side, the side China landed on, is mostly bright, heavily cratered highlands. Craters on top of craters, far fewer smooth lava plains, much rougher terrain. Visually it looks older and more damaged. That difference is not just at the surface. When scientists model crust thickness, the far side crust comes out much thicker, often around 60 to 80 kilometers, roughly 37 to 50 miles. Parts of the near side, especially under Big Maria, are closer to 30 kilometers, about 19 miles. So you have one hemisphere where the crust is thick and harder to crack, and one hemisphere where it is thinner and easier for magma to reach the surface. For decades, this was a major unsolved problem. Why would one side of the same moon end up armoured and the other side end up broken and flooded with lava? What in the moon's early evolution could cause that? So that if you want to attack that problem, where do you go? Do you land anywhere on the far side and just start measuring? China chose a much more targeted approach. They aimed Chang'e 4 straight at one of the most extreme structures on the moon, and actually in the whole inner solar system. The landing site is von Kármán crater, about 186 kilometers wide, roughly 115 miles across. But von Kármán itself lies inside something much bigger, the South Pole Aitken basin, usually called SPA. SPA is huge, around 2,500 kilometers in diameter, about 1,550 miles, and up to about 13 kilometers deep, around 8 miles. That's almost a quarter of the moon's circumference in one impact structure. It is one of the largest and oldest known impact basins anywhere nearby. So why is landing there such a big deal? A basin that large would have excavated material from deep inside the moon, from the lower crust and maybe even the upper mantle, and spread it around. Then later impacts like von Kármán punched into that already thinned and disturbed region, digging even deeper. By landing on the floor of von Kármán, you're not just sampling the top few meters of some random patch of crust, You're standing on the overlap of multiple giant impacts that have already done a lot of the drilling for you. The plan was aggressive but clear. Use one big crater inside an even bigger basin to expose deep material, and then send a rover to measure it directly. But there's another problem you can't ignore. On the far side, Earth never rises above the horizon. That means you can't send commands or receive data directly with a normal radio link. A lander on the far side is completely blocked by the bulk of the Moon from any ground station on Earth. Without a workaround, you land once, you lose contact, and the mission is dead. China solved this by placing a relay satellite, Queqiao, in a special orbit around the Earth, Moon L2 point, about 65,000 kilometers beyond the Moon. L2 is a gravitational balance point where a spacecraft can stay in a stable looping orbit and maintain line of sight to both the far side landing site and Earth at the same time. So now the path is rover and lander talk to Queqiao, Queqiao talks to Earth. Every picture, every radar scan, every spectrum bounces through that relay. With that network in place, Chang'e 4 made its landing on the 3rd of January 2019, touching down on the floor of von Kármán. This was the first soft landing on the far side of the Moon in history. A few hours later, the U-22 rover drove off the lander. It weighs around 140 kilograms, about 310 pounds. It moves slowly, about walking speed, but speed is not the point. It carries instruments that can see beneath the surface and read the chemistry of rocks and soil. U-22's payload includes lunar penetrating radar, which sends radio waves into the ground and records echoes from buried layers down to hundreds of meters. It also carries visible and near-infrared spectrometers, which look at reflected sunlight from rocks and soil and break it into wavelengths. From those spectra, scientists can estimate mineral types and oxide contents, things like iron and titanium levels, and distinguish between highland and orthosite, mare basalts, and deeper, more exotic material. So this isn't just a flag-planting exercise. This is a mobile lab driving inside one of the biggest scars in the solar system, mapping what lies above and below the surface in high detail. It is literally giving numbers to questions that before this were just models and best guesses from orbit. Now, why does any of this matter to you personally beyond space fan curiosity? The South Pole Aitken Basin is probably one of the oldest impact structures on the Moon, maybe older than 4.2 billion years. It formed during the period when the inner solar system was still full of large impactors, hitting Earth, the Moon, Mars and other bodies at high speed. Earth went through that same bombardment, but our planet has erased most of the evidence with plate tectonics, erosion and oceans. The Moon has not. That means the far side, and SPA in particular, is like a long-term storage system for events Earth can no longer remember. The rocks there record how often big impacts happened, how deep they dug, how much they heated the crust, how long it took surfaces to cool and stabilize. Those details feed back directly into questions like, when did Earth's crust become stable enough for long-term oceans? When could early life survive without being constantly wiped out? How fast did the environment calm down? By putting Chang'e 4 and U-22 into von Kármán, China effectively opened a physical archive of that history. Instead of only relying on blurry orbital data and gravity maps, scientists now have in situ measurements from a rover actually driving on the floor of SPA, on the thick, old far-side crust that has been through multiple giant impacts. And here's the real shift. Once you have those measurements, the Moon stops being a simple grey ball with some dark spots and becomes a two-faced record of planetary evolution. One hemisphere thin, hot and lava-flooded, the other thick, cooler and impact-dominated. The far side, the side you never see from Earth, turns out to be the key to understanding why those two faces exist at all. But to really see that difference, you have to read the far side landscape like a crime scene, where every crater, every buried layer, every boulder carries a timestamp and a clue. And that's exactly what U-22 started to do once it began to roll away from the lander into a surface that is not just rough but extremely old and extremely complex. How do you read a place where nothing moves, nothing grows and nothing erases the past for billions of years? On the far side of the moon, the only thing that really changes the surface is impact after impact. So every crater is basically a clock, and the whole landscape is a timeline punched into rock. Here's the logic: the more craters you see in a region and the more worn down and soft-edged they are, the older that surface is. A fresh crater has sharp rims, steep walls, and clean ejecta around it. Over time, new impacts chip at it, landslides soften the edges, micrometeoroids grind the walls. On the far side, especially inside South Pole Aitken, the ground is absolutely covered in craters on top of craters, from little pits just centimetres across, up to basins hundreds of kilometres wide. There's barely any clean, smooth patch. That crater saturation tells you something very direct. Huge regions of the far side have not been resurfaced by lava flows for an extremely long time, billions of years. The near side's big dark maria are younger, lava poured out and covered older scars. On the far side, especially where U22 is driving, you're looking at surface layers that have basically sat there, getting hit and re-hit since the early solar system. In plain terms, these are some of the oldest exposed surfaces you can walk on anywhere near Earth. So if the entire area is that old, what does that mean for the specific spot China chose, von Kármán crater? Conceptually, put yourself there for a second. You're standing in the middle of a crater about 186 kilometers wide, around 115 miles, which itself sits inside the SPA basin, about 2,500 kilometers across, roughly 1,550 miles. It's a crater inside a much bigger crater, inside a hemisphere that is already heavily damaged. The floor of von Kármán is deep, about 6 kilometers below the average lunar radius, so you're sitting roughly 6 kilometers down from a perfect sphere, around 20,000 feet, almost twice the cruising altitude of a small private jet. And models say the crust directly under that floor might be less than about 10 kilometers thick, around 6 miles, much thinner than typical far-side crust. Why does that matter? Because the depth of a crater controls how deep it dug into the moon. A structure this big, sitting in a basin that was already thinned and modified, could have excavated material from the lower crust, or maybe even from the upper mantle, then splashed it up toward the surface. So when U22 is driving around on that crater floor, the rocks under its wheels might not just be local surface crust, they might be pieces from deep layers that you normally never get to see without drilling. But there's another layer to this, literally. When U22's cameras started sending back images, one of the first things that stood out was how rough and cluttered the landscape is. The ground is packed with boulders around a metre across, smaller cobbles, and fine dust all mixed together. It's not a smooth lava plain, it's a debris field. Look closer, and many of those blocks are not just scattered randomly. They sit in subtle ridges, arcs, and chains. When you trace those patterns backward on a map, a lot of them line up with distant craters like Finsen, von Karman L, and Antoniadi, some of them more than 300 kilometers away, around 185 miles. That tells you the surface here is not made only from rock that formed right underneath your feet. It's a mashup of ejecta, material thrown out by multiple impacts, flying hundreds of kilometers and landing here. So the ground under U22 is a mixture, local crust plus debris from several different source craters, piled and reworked over time. That complicates the story, but it also makes the site more valuable because you can sample material that originated over a wide region of SPA, not just one small patch. Shape and distribution are one side of the story. The other side is chemistry. The far side highlands, including the area around von Karman, are dominated by a rock type called an orthosite. That's a light-coloured, feldspar-rich rock that formed very early, when the moon was mostly molten. As the global magma ocean cooled, lighter plagioclase minerals floated up and froze into a thick crustal lid. That's what you see as bright highlands. The nearside Maria are very different. Those dark plains are basalt, iron and titanium-rich lava that came up later from the interior, filled in big basins and cooled into dense, dark rock. When you look at them from orbit, they absorb more sunlight. They look like dark seas on the face of the moon. U22 carries a spectrometer that looks at the light reflected from rocks and soil at many wavelengths. By comparing those spectra from von Karman with data from near-side landing sites and orbital maps, scientists see a different mix of minerals. The far-side site shows strong highland signatures and very little sign of the ultra-dark high titanium basalts that dominate places like Mare Tranquillitatis on the near side. In simple terms, the far side is saying very clearly, my volcanic story is not the same as the familiar face you see from Earth. So here's the key question. Is the far side just an older version of the same moon, or is something deeper going on? When you combine all these clues, crater ages, crust thickness, surface roughness, and chemical fingerprints, a stronger pattern appears. The far side seems to have had less internal heat, fewer and smaller lava floods, and a crust that stayed thicker for longer and resisted cracking. It got hammered by impacts, but it did not respond with huge oceans of lava the way the near side did. Later missions, like Chang'e 6, which brought samples back from another part of the SPA region, reinforced this. Those far-side lavas show signs of having crystallized at cooler temperatures than similar near-side lavas, and the region looks poorer in heat-producing elements like uranium and thorium. That means the far side's interior did not have as much built-in heater power over time. It cooled faster, it stayed more rigid, and it produced less volcanic resurfacing. That difference is not cosmetic. It means the moon's two hemispheres evolved under different thermal regimes, different internal heat budgets, different crust structures, even though they are part of the same body. Any serious model of how the moon formed from an early giant impact, how its magma ocean cooled, and how its crust and mantle separated, now has to explain not just a moon, but a moon with a split personality, one hot, thin and flood-prone, the other cooler, thick and impact-dominated. And that raises the next level of tension. If the surface already shows you this much asymmetry, what happens when you stop just looking at craters from above and start probing down tens to hundreds of meters under the rover's wheels? Because that's what U22's radar does, and what it finds below the surface is even more extreme than what you see on top. So if the surface already looks extreme, what happens when you find out the ground itself is way deeper, stranger and harder to handle than anything Apollo ever saw? The answer starts with one simple number, and it changes how you think about living on the far side at all. On the near side, at the Chang'e 3 landing site, China measured a regolith layer only a few meters thick, a loose blanket of dust and small fragments sitting on harder material. That matches what Apollo and other missions suggested, a thin layer, still tricky but manageable. On the far side, at the Chang'e 4 site, U22's radar and thermal measurements say, no, this is a different world. At the landing region in von Karman crater, the regolith is around 12 meters thick, about 40 feet. That is roughly the height of a 4-story building, but here it is not steel and concrete. It is 12 meters of shredded rock, dust and rubble. When you hear regolith, think of a mixture, not one uniform material. You have ultra-fine dust, sand-sized grains, sharp glassy shards, and small rock fragments all mixed together, all created and reworked by billions of years of impacts. Every hit breaks rock, melts some of it, sprays it out, and then later impacts grind the ejecta even finer. On the far side, that process has gone on for so long, without big lava floods to reset the surface, that the rubble blanket has grown very thick. U22's data basically tells you you're not dealing with a thin coating over bedrock, you're driving on a deep, loose, multi-layered pile. Now, thickness is only part of the story. You also need to know how dense this stuff is, from top to bottom, because that controls how it holds heat, how it supports weight, and how radar waves move through it. U22's team combined two kinds of measurements: how fast the surface heats up and cools down during the long lunar day and night, and how radar pulses reflect from different depths. From that, they can estimate how tightly packed the grains are at different levels. The very top layer, roughly the upper 30 centimeters, about 1 foot, comes out with a bulk density around 1,300 kilograms per cubic meter. For comparison, typical concrete is closer to 2,300 to 2,400 kilograms per cubic meter, so the top is relatively light and fluffy. As you go deeper, down past about 6 meters, around 20 feet, the inferred density climbs toward 1,900 kilograms per cubic meter. That's much more compact. In everyday terms, the top tens of centimeters behave like a powdery snowpack made of crushed glass and fine grit, easy to disturb, easy to kick up. Deeper down, the material becomes more like tightly packed rubble, broken bricks, forced together under their own weight, with fewer empty spaces between pieces. For a rover, that means you have soft, slippery stuff on top, but a progressively stiffer, more supportive structure underneath. For engineers thinking about landers, drills, and habitat foundations, those numbers are critical. You might assume that with a rover driving around and a lander firing its engines at touchdown, the soil must be churned deeply, mixed, and disturbed over meters of depth. The radar says that is not true. When scientists look at how the radar scattering changes right under U-22's tracks, they find that the disturbed zone is surprisingly thin, on the order of 0.20 meters, plus or minus about 0.06 meters, so roughly 20 centimeters thick, a bit less than the length of your forearm. That means nearly all of that 12-meter column below the surface, maybe 11.8 meters out of 12, is still geologically undisturbed in any modern sense. It has been reworked by impacts over billions of years, yes, but the layering produced by different events is still there. You have a stratified record, impact over impact, ejecta over ejecta, thin lava units mixed in, all preserved in depth. For science, that is huge. It means the subsurface is not just random rubble, it is a history book stacked vertically, and the rover's radar lets you read the chapter breaks. Look again at the surface itself, and you see another important clue. The area around Changafor is not a smooth dust field. It is cluttered with rocks from about 10 centimeters up to a meter across, so from fist-sized chunks up to boulders roughly the size of a big household appliance. Those are real driving hazards for a small rover. You need careful path planning, or you risk high-centering the vehicle or putting too much load on a wheel. But that rock abundance is not just an operations problem, it is a data point. The ratio of rocks to fine dust affects how the surface takes in sunlight, how fast it radiates heat back out at night, and how radar pulses scatter. Areas with more exposed rocks cool faster at night, and they generate stronger radar echoes from near the surface. Over long timescales, micrometeoroid gardening gradually breaks big rocks into smaller ones and eventually into dust. So if you still see lots of substantial blocks, the ejecta they came from may be comparatively younger or more recently exposed. Compared to the smoother near-side Maria, where thick lava flows buried a lot of older ejecta and then got worn down into relatively level plains, von Kármán looks rough, jagged, and raw. The boulder fields and uneven ground tell you that you're standing on material that is still very close to its impact origin. Shredded crust and possibly mantle material, not calm, flooded lava seas. Again, the site is screaming at you. This is ejecta country, not mare country. Now, think forward. If you start talking about a human base on the far side, especially in or near South Pole Aitken, this 12-meter rubble blanket becomes a double-edged tool. On the positive side, it is an excellent radiation shield. If you excavate only 3 to 5 meters down, roughly 10 to 15 feet, and cover a habitat with that much regolith, you can cut cosmic ray exposure dramatically. The mass above you blocks charged particles and high-energy photons, turning the loose rock into a natural bunker. You do not need to haul tons of metal from Earth. You can use what is already lying there. On the negative side, that same deep, loose mixed layer makes engineering harder. Landing pads have to handle rocket plumes kicking up sharp dust and small fragments, which can fly at high speed and sandblast equipment. Foundations for habitats, antennas and telescopes have to be designed so they do not sink, tilt or shift in a material that is soft at the top, denser below and not uniform in any direction. Drilling rigs need to cope with changing density, sudden rocks, and unknown voids. Every structure has to handle the fact that you are building on a pile of debris, not a solid slab. So when you put all this together, the far side soil is telling you something very clear, in plain language. It is older, thicker, and more chaotic than the near side sites humans have worked with so far. It stores more history, it offers more natural shielding, and it delivers more engineering headaches. If you want to put people, telescopes, or industry out there, you cannot copy-paste near-side plans. You have to design for this specific environment, or it will punish your assumptions. And that leads directly to the next step. If the top 12 meters are already this complex, what do the radar echoes say about the structure hundreds of meters down, about buried craters, hidden lava layers, and ejecta from impacts you cannot see on the surface at all? Because once you start treating the subsurface as a 300-meter deep cross-section, the moon's far side stops being just thick soil and turns into a stacked record of extreme events. How do you explore hundreds of meters under the ground when you can't drill even a single meter? On the far side, U-22 solves that with one of the most important instruments on the whole mission, lunar penetrating radar. And this is where the moon starts to look less like a flat surface and more like a 3D stack of violence. Here's how that radar actually works, in simple terms. U-22 sends short bursts of radio waves down into the ground, then measures how long it takes for echoes to come back from buried layers and rocks. Different materials and different boundaries between materials reflect those signals in different ways. Time delay gives you depth in meters, echo strength and shape tell you how sharp a boundary is and how rough it is. The system uses two main channels. The lower frequency channel, called CH1, goes deep, more than 300 meters down, roughly 1,000 feet. The signal is long wavelength, so it can punch through a lot of material, but the detail is coarser. You see big structures, thick units, and major boundaries. The higher frequency channel, CH2, has much finer detail, but can only see down about 35 meters, around 115 feet. That one is like zooming in on the shallow subsurface, where the rover's tracks and nearby boulders matter. You trade depth for resolution, but together the two channels give you a vertical profile from the loose topsoil all the way into the deep interior of the crater floor. So what does that profile actually look like under your feet at the Chanka 4 site? When scientists stack the radar data along U-22's path, a clear layered structure shows up. At the top, down to about 12 meters, you get the regolith layer you heard about before, fine, chaotic, heavily fractured material, full of small clasts, dust and glass. This is the zone that has been churned by micrometeoroid hits and small impacts for billions of years. It looks messy in radar, with lots of small irregular echoes. Below that, the signal changes. From around 12 meters down to a few tens of meters, the radar sees a zone with stronger, more discrete reflections, consistent with coarser, blocky material and buried boulders. This is where larger chunks of ejecta dominate, pieces tens of centimeters to meters across, mixed in with finer matrix. It's not solid bedrock, but it is a more structured rubble, less fluffy than the upper regolith, more like a pile of rocks buried under sand. Deeper still, CH1 shows thick units with clearer, more continuous reflections, extending down to hundreds of meters. These deeper packages are interpreted as stacked ejecta blankets and possibly thin lava flows, laid down by major impacts and later volcanic episodes, then buried again by the later events. So under the rover you effectively have three main regimes: loose regolith at the top, a coarse blocky transition zone, and then big deeper units that represent giant events in the moon's past, all sitting on top of each other. If that sounds like a simple sandwich, the next step ruins that idea quickly. The radar does not just see flat horizontal layers, it also picks up curved, concave shapes and breaks in the continuity of those reflectors. Some echoes bend downward and then fade, forming lens-like patterns. Others are truncated abruptly, as if something cut across them. Those features are classic signatures of buried impact craters and their rims. In other words, below the lander site, you're not just seeing one clean layer of ejecta, then another, neatly stacked. You're seeing ejecta filling old craters, new craters punching into older deposits, and later materials draped over everything again. At least several large impacts must have hit this area after von Kármán and the main SPA basin formed, each resurfacing the region, adding new ejecta blankets, breaking and burying older structures, but never quite erasing them fully. So when you look at the radar data, you are looking at a kind of overwritten document where each big explosion adds a new chapter, but the older writing is still faintly visible underneath. It's a palimpsest made of rock, and LPR lets you separate those drafts by depth and geometry. The obvious next question is, whose ejecta are you actually standing on? Is everything under U22 sourced from von Kármán itself, or is it a mixture from several far-off scars? To answer that, scientists don't just stare at the radar by itself. They match the depth of layers and the inferred rock content with the regional maps of known craters, their expected ejecta thicknesses, and what directions their debris should have flown. When they do that, a pattern appears. A lot of the material below the rover is best explained as ejecta from nearby but distinct craters like Finsen, which lies to the northeast, and possibly older and others around the edge of SPA. These are big energetic impacts in their own right, capable of excavating material from deep crust or even mantle, then throwing it tens to hundreds of kilometers, 60 to 300 plus miles, across the basin. That means the stuff beneath you inside von Kármán is not just local floor material. It includes rock dug out from deeper layers far away, transported ballistically through low lunar gravity, and then buried under later impacts. The radar is effectively telling you that the subsurface here is a mixing zone for deep materials from multiple sources, not just a cross-section of one vertical column of crust. This is exactly why Chang'e 4 is such a big shift in how we use the Moon as a recorder of solar system history. Before this mission, most models of the far side subsurface were built from orbital imagery and gravity data. You could see surface shapes and inferior mass distribution, but you had no direct, high-resolution in-situ profile of how layers are stacked at a specific site. You were guessing, even if they were educated guesses. Now with U22's radar traces tied to actual surface rocks, actual regolith thickness and actual densities, you can anchor those models. You can say, at this point on the floor of von Kármán, there is about 12 meters of loose regolith, then tens of meters of blocky ejecta, then multiple deep units that probably belong to ejecta from Finsen and other craters, and you can put depths on all of that in meters and hundreds of meters. That does three important things at once. First, it lets you calibrate crater counting ages. If you know a buried crater's ejecta appears at a certain depth and is overlain by another unit with a known age, you can lock down the timeline more tightly. Second, it sharpens your picture of how far ejecta really travels for a given impact size, which feeds into models of how often deep material is brought to the surface. Third, it forces you to rethink how local any lunar rock sample really is, especially on the far side. A rock under your rover might have been born hundreds of kilometers away and tens of kilometers deep. So the far side stops being a simple static cross-section and instead becomes a giant mixing bowl, where crust and mantle, near and far, old and less old, are all thrown together in layers you can now actually resolve. And that sets up the next, more uncomfortable question. When U22 starts spotting rocks with unusual chemistry on the surface, are you just looking at weird crust, or did the rover actually roll over material from the Moon's mantle itself? How do you tell if a rover has touched rocks from the Moon's mantle when it never drilled more than a few centimeters into the ground? On the far side, the answer is simple but uncomfortable. You stop staring at the soil, and you start interrogating individual rocks for the fingerprints of the deep interior. If you want to know what the inside of a rocky world looks like, you go hunting for one key mineral, olivine. It's a magnesium-rich, usually greenish mineral that dominates the upper mantles of Earth, the Moon, and many asteroids. The crust is more feldspar-heavy, the mantle is more olivine-heavy. So if you can prove you're looking at rocks rich in olivine and relatively poor in feldspar, you're suddenly in deep interior territory, not just surface crust. U22 carries a visible and near-infrared spectrometer, basically a device that looks at sunlight reflected off a rock and breaks it into many wavelengths. Different minerals absorb and reflect light in distinct patterns. Olivine has clear absorption bands at specific near-infrared wavelengths. Feldspar has a different signature. Pyroxene has its own. When scientists looked at some of the rocks along U22's path, the spectra didn't match typical highland crust. They matched olivine-rich norites, rocks you expect from lower crust or upper mantle, not from standard far-side surface material. That's like checking under the hood of a car and finding parts that normally live deep in the engine sitting on top of the bodywork. One rock in particular turned up as a problem for the simple cost story. It was roughly suitcase-sized, not huge, but big enough to give a clean spectrum sitting alone on the regolith. When U22's spectrometer scanned it, the signal was dominated by strong olivine features and showed low plagioclase content, meaning not much feldspar. It didn't look like the commoner orthositic highland rocks that dominate the far side. It also didn't match the composition of ordinary mare basalt, the dark lava from the near side. So you're left with a boulder that does not fit the obvious local categories. The most straightforward explanation is that it did not form where it is. Researchers argue it was excavated from tens of kilometers deep by a large impact somewhere in or near SPA, thrown out as part of an ejecta curtain, and eventually deposited on the floor of von Kármán. Later impacts and regolith processes moved it a bit, but not enough to erase its deep signature. At this point, the key question becomes, could the impacts around von Kármán realistically dig that deep? You don't guess that, you use impact scaling laws, relationships that tie crater diameter to excavation depth. For a crater around 180 kilometers across like von Kármán, typical models say it can excavate material from depths on the order of 12 kilometers or more, roughly 7.5 miles. That already gets you into the lower crust. Now stack that on top of the SPA event. You have a basin almost 2,500 kilometers wide, about 1,550 miles, which massively thinned and disturbed the crust in this region billions of years earlier. That first hit weakened and excavated the area. Then von Kármán blasted into that already disturbed zone like a second drill going into a pre-drilled hole. Together, those two impacts give you a realistic pathway for material from very deep layers, maybe even from the upper mantle, to end up close enough to the surface that ejecta blocks can be parked where a small rover can see them. You're not getting pieces from 1,000 kilometers down, but tens of kilometers is absolutely on the table. If those olivine-rich rocks really are mantle or deep lower crust samples, the implications go far beyond one crater. They become direct physical tests of how the moon separated into layers in its early life. The standard picture says the moon started out with a global magma ocean. As it cooled, heavy iron-rich minerals sank to form the mantle. Lighter plagioclase floated up to form the crust, and leftover enriched liquids with odd elements pooled in between. That's the textbook. Now, with actual deep origin rocks in your hand, you can check it. Their composition tells you how much iron and magnesium the mantle holds, how much it has melted since, and what trace elements got concentrated where. You can compare that to Earth's upper mantle and ask, is the moon just a stripped-down chunk of Earth, or did its magma ocean behave differently? Those answers feed straight back into the giant impact theory, which says the moon formed when a Mars-sized body hit the early Earth at high speed and sprayed material into orbit. The chemistry of deep lunar rocks is one of the only hard tests you have for that scenario. But here's where the story stays honest, and the tension goes up instead of collapsing into a clean headline. Not everyone agrees that these rocks must be mantle. Some scientists argue they could be unusual lower crust intrusions, bodies of olivine-rich magma that pushed up into the crust and solidified there, rather than pure mantle chunks brought to the surface. In that view, you are still seeing something special and deep, but not necessarily naked mantle. That disagreement is not a failure, it's actually valuable. Even the fact that serious people can't settle this instantly tells you that the crust and upper mantle under SPA are not simple. They're not one smooth transition from an orthosite on top to uniform mantle below. Instead, you're dealing with a chemically complex layer cake, with different rock types, different cooling histories, and different melt pockets frozen in at various depths. The important shift is this: you are no longer talking about that complexity in vague terms like heterogeneous interior or anomalous region based only on blurry orbital maps. You now have real mineral IDs, real olivine bands in real spectra, real magnesium and iron estimates, tied to specific rocks on the ground. You have a context, a crater chain, an ejecta path, and a radar-mapped subsurface under each rock. The far side has moved from grayscale pixels to hard numbers, and that sets up the next hit to your expectations, because while everyone was arguing about whether U22 had just rolled over Mantle, the rover also stumbled on something that went completely viral on Earth, a so-called gel-like substance in a small crater. Headlines screamed, people imagined weird goo on the moon, and suddenly the most sensational explanation was the one getting all the attention. The reality turned out to be different, more ordinary in one sense, and yet much more important for understanding how violent impacts really reshape the far side. In 2019, U22 looked into a small crater and saw something that did not match the usual grey, dusty picture of the moon at all. Inside that little pit, just a few meters across, there was an oddly coloured shiny patch. Chinese reports described it as gel-like, and that single phrase blew up everywhere. Suddenly you had headlines talking about lunar slime, strange goo on the far side, maybe some exotic pool of lava that somehow stayed soft. The reality was much more direct and honestly more interesting. Under harsh, high-contrast lighting, what the rover was seeing was a dark, glassy material that reflected light differently from the surrounding dust, so it popped out in the images as something unusual. So the real question was simple. Is this actually something physically weird, or just normal high-energy impact physics seen up close for the first time in this region? To answer that, you don't guess from photos, you look at the spectrum. U22's visible and near-infrared imaging spectrometer, VNIS, was pointed at the patch. When the data came back, it was clear that this gel was not gel at all. It was rock, specifically impact melt breccia. Here's what that means in plain language. When an impactor hits the moon at very high speed, something like 15 kilometers per second over 30,000 miles per hour, the energy dumped into the target rock is enormous. Local temperatures can spike so fast that part of the rock literally melts on the spot. At the same time, other parts are shattered into fragments. If the energy and geometry are right, you end up with a pool or splash of molten material that traps broken pieces inside it. That mix cools and hardens into a solid, a glassy matrix of frozen melt with included rock fragments. That's impact melt breccia. VNIS saw exactly that signature. A dark, glass-rich material with embedded clasts. Not water, not ice, not anything biological. So the dramatic gel label was wrong in a strict sense, but the feature was still a clear marker that this area had seen intense, fairly recent impact activity on a small scale, right in front of the rover. If it's just solid rock, then why did it look wet or gooey to so many people, even to trained eyes at first glance? That comes down to geometry and lighting. The crater itself was small, only a few meters wide. The melt had pooled into a low lump on the floor. A dark, glossy patch separated from the lighter, dusty regolith around it. From U22's low camera angle, and with the camera set to high contrast to capture detail in both bright and shadowed areas, the reflective surface of that melt patch flashed back more light toward the rover. So you ended up with a shiny high-contrast blob in the middle of a muted background. In that view, your brain defaults to wet or gooey because that's how shiny patches on rough ground usually work in your everyday life. But physically, this is closer to cooled road tar or dark, glassy asphalt. Solid but reflective, not a puddle. The key science point is not the illusion of liquidity. It's that this melted material records the chemistry of both the impactor and the local target rock in one place. It's a mixed sample of what got hit and what did the hitting. This is not the first time humans have met this kind of material on the moon. Apollo astronauts on the near side, especially Apollo 17, collected dark glassy impact melts and tiny colourful glass beads formed in high-energy impacts and fire fountains. Those samples showed that violent impacts and short-lived eruptions can create glass phases that trap details about temperature, pressure, and composition. What U22 found is the far side version of that process, but in a very different geological context. Instead of sitting in younger nearside Maria, you're in the floor of South Pole Aitken, in crust that is older, thicker, and more deeply excavated. The same basic physics is operating, but the target rocks are different, the crustal layers involved are different, and the history of impacts is different. That means when you compare impact melts from near side and far side, you can start to see how composition shifts when you punch into different types of crust and different depths. So the gel patch, once you strip away the hype, becomes another data point in a much bigger pattern. SPA region impacts are energetic enough and frequent enough over the time to melt and remix deep materials, then freeze those histories into glassy rocks. You can analyse them wavelength by wavelength, look at their mineral signatures, measure their iron and titanium contents, and figure out which layers they sampled. And that is the real shattering insight here. The public story was, maybe there's something mysterious and soft on the far side. The scientific story is stronger. You are looking at hard evidence that this region regularly experiences impacts intense enough to melt crust and possibly mantle-derived material together, then lock that high-pressure, high-temperature history into solid rock. This is the same pattern you've seen across the whole mission so far. Big headline, simple hook, then a deeper, more demanding reality that actually tells you how the moon works. The gel wasn't a one-off oddity. It was a local snapshot of the same brutal process that built those thick ejecta layers, that buried craters under other craters, and that may have brought mantle-like rocks to the surface. And once you accept that SPA can melt and remix material this violently, the next logical step is to stop just talking about shapes and textures and start talking about chemistry and numbers, heavy elements in the dust, titanium and iron levels in the soil under U22's wheels, and what that chemical map says about how extreme the far side really is compared to the face you grew up looking at. You've seen that the rocks on the far side look different, and the layers under the rover are stacked and messy, but the real punch comes when you start putting numbers on the chemistry of the dust itself. Once you measure what heavy elements are actually in the soil along U22's path, it stops being just old highlands and turns into something much more extreme. When researchers took U22's VNIS data and combined it with calibrated images, they could estimate how much titanium oxide and iron oxide, TiO2 plus FeO, are in the regolith along the rover's track. They focused especially on sections between about 300 to 500 metres from the lander, and again between about 1,000 and 1,150 metres, so roughly 1,000 to 1,600 feet away. In those stretches, the inferred TiO2 plus FeO levels were higher than you expect for normal far-side highland soil. Typical highland anorthosite should be relatively low in these oxides, but the numbers here point to a strong input from basaltic material and SPA-related ejecta. In plain terms, the chemistry says, this is not pure floated crust from the early magma ocean, it is mixed with darker, heavier lava-type material. That creates a direct contradiction with the naive picture of the far side. The standard line is, the far side doesn't have big dark seas like the near side, so it must be mostly clean highlands, bright feldspar-rich, with little basalt. U22's spectra cut into that. The far side may lack huge continuous mare like Mare Imbrium, but the soil where the rover drives is full of basalt fragments, hidden in the mix. They're not forming vast lava oceans, they're chopped into clasts and blended into the regolith. This fits the radar story perfectly. LPR told you there were multiple ejecta blankets and maybe thin lava layers stacked and then shredded under von Kármán. The chemistry now backs that up. You're not standing on a simple highland crust with one composition. You're standing on ground that is literally a crushed mixture of ancient lava flows, deep crust, and possibly mantle-influenced rocks, all thrown together by impacts and then ground up over billions of years. Every handful of soil is a composite sample of that history. Zoom out a bit. Even before Chang'e 4, orbital missions like Clementine and Lunar Prospector showed that the South Pole Aitken basin has a weird geochemical fingerprint. It looked poorer in the heat-producing elements like potassium, thorium and uranium than some near-side regions, and it showed a different balance of iron and titanium compared to the Big Maria. But those were broad, low-resolution maps, built from pixels tens of kilometers wide. You could tell SPA was different, but you couldn't say exactly how that played out in the rocks on the ground. Now U22's in situ spectra lock those orbital hints to reality. When VNIS tells you that a particular patch of soil 400 meters from the lander has a certain TiO2 plus FeO content, you can connect that to a specific pixel in an orbital map and adjust that map. Instead of just labeling a region dark or slightly enriched in iron, you can assign real oxide percentages tied to real rocks you've actually measured. That turns SPA from a fuzzy anomaly into a region where you can write down concrete chemical profiles. You might ask, why care about these oxide numbers at all? Why does it matter if the soil has a few percent more FeO or TiO2? The answer is, those oxides control a lot of the moon's behaviour. Iron oxide and titanium oxide influence how dense and dark a lava is, how easily it flows, how quickly it cools, and how strong it is after it solidifies. High titanium basalts, like some on the near side, are darker, denser, and absorb more sunlight, which changes how much heat they hold and how they show up in gravity data. Regions like the Procellularum creep terrain on the near side, with their odd combination of radioactive elements and certain lava chemistries, are tied to those kinds of oxide patterns. On the far side, the different FeO and TiO2 balance says the volcanic plumbing and the heat budget evolved along another track. Less of the hot, enriched material that feeds long-lived volcanism, more of the cooler, thicker crust that resists repeated flooding. That lines up with the picture you already saw from crater counts and crust thickness, but now it's backed by actual chemistry in the soil. The two hemispheres didn't just end up with different shapes by chance, they ran on different internal fuel levels. So when you hear TiO2 plus FeO, don't treat it as a random formula. Translate it into something you can feel. The Regolith U22 drives over is chemically closer to weathered basaltic gravel than to bright, clean granite-like sand. In metric terms, you're dealing with tens of weight percent of these oxides in many spots, not just traces. In more intuitive terms, think of standing on ground that has the darkness and heft of a volcanic beach, rather than the pale, powdery look you associate with the classic Apollo photos. Put all of this together and the message tightens again. The far side around SPA and von Karman is not just a thick old highland crust with a few random odd rocks. It is a chemically extreme environment where heavy element content, impact melting and deep excavation have produced soils that are richer, darker, and more mixed than you would guess from orbital images alone. The heavy metals in the dust are telling you that the interior here cooled differently, bled lava differently, and stored heat differently from the near side. And once you care about those oxide levels, you're forced straight into the next question. How does this chemically extreme soil actually respond to the brutal temperature swings on the far side? Because if the composition and porosity are different, the way it stores and releases heat is different too, and that directly determines how survivable or deadly this place is for hardware and for people. How hostile is the far side if you strip away the sci-fi and look only at the numbers? At the Chang'e 4 site, the lander's instruments watch the ground go through temperature swings that your body and most Earth hardware simply could not survive. In local lunar daytime, the surface climbs well above 100 degrees Celsius, easily past the boiling point of water at sea level, over 212 degrees Fahrenheit. During the long lunar night, it drops below minus 170 degrees Celsius, colder than minus 274 Fahrenheit. You're looking at a change of about 270 degrees Celsius over each 29.5-day lunar cycle. On Earth, most electronics and materials are designed for maybe a few tens of degrees range, not hundreds. Expose them to this kind of heat and cold without serious protection, and they will crack, warp, or just stop working. For scientists, though, those brutal swings are not just a problem, they're a tool. By tracking exactly how fast the soil warms up after sunrise and how fast it cools after sunset, you can work backwards, or invert, the temperature curve to estimate how efficiently the regolith conducts heat down into the ground and back up. That efficiency is called thermal conductivity, and combined with how quickly or slowly the temperature responds, the thermal inertia, it tells you a lot about what the soil is like physically. Solid rock, with very few pores, heats up and cools down more slowly than a fluffy, highly porous layer. Ultrafine, very loose dust reacts fast. Lunar regolith sits in between, and on the far side at this site the details matter. When you combine the temperature behaviour with the density estimates from earlier, a clear picture forms for the upper layer. The regolith's thermal inertia is lower than solid bedrock, but it is higher than a cloud of ultrafine powder. That points to something in between, a material with lots of tiny voids between grains and clasts, but still enough contacts between particles to move heat downward. In simple terms, the upper layer acts like a very porous, rough mixture of glass and rock fragments, more like a bed of pumice gravel than a solid concrete slab. For hardware, that means the surface responds quickly to sunlight, getting hot fast, and then radiates that heat away quickly once darkness returns, while deeper layers change more slowly. For future habitats, you care about that gradient because it tells you how deep you have to go before the temperature swings start to smooth out and become less deadly. The strong result here is that the thermal data and the radar data are telling the same story. LPR showed you a low-density, very fractured upper 12 meters, then a more blocky, compact zone, then deeper units with even higher density. The temperature behaviour agrees. As you go deeper, both the inferred thermal conductivity and the bulk density move towards around 1,900 kilograms per cubic meter, which is much closer to compacted rock. So the moon at this site is literally fluffier on top, more like a loose rubble blanket in the upper meters, and more rock-like below, with fewer voids and stronger heat flow. And now you can put numbers and depths on that transition, not just hand-wave it. In metric, you're talking about the first metre or two being highly porous, then a steady tightening with depth down to tens of metres. In imperial, the top few feet are the loosest, and by 20 to 30 feet down, things are already noticeably more compact. This surface behaviour links directly to what's happening deeper inside. Chang'e 6, which brought back samples from another site in the South Pole Aitken region, adds a crucial piece. When scientists reconstructed the crystallization conditions for farside lavas from those samples, they found that they formed at temperatures about 100 degrees Celsius cooler than comparable lavas on the near side, roughly 180 degrees Fahrenheit lower. That is a big offset in planetary terms. If farside lavas needed lower temperatures to crystallize, that implies the farside interior on average was cooler. It didn't store as much heat, it didn't keep large magma reservoirs active for as long, and it didn't produce the same scale of huge mare floods that you see dominating the near side. That matches what you already see from the lack of big dark seas and from the crust thickness measurements, but now it's backed by actual sample thermometry, not just models. So you can now say with some confidence that the far side's crust stayed thicker, the mantle beneath it stayed cooler, and the surface spent more of its time being shaped by impacts than by flowing lava. Lava showed up, yes, but it didn't reset the landscape in the same way it did on the near side. On the far side, old impact scars survived longer. Regolith had more time to grow deep and porous, and the surface became a better long-term recorder of impact history. When you put all of this together, the message is not just the moon is a bit lopsided, it's much stronger. You're looking at one small body that cooled and froze in two very different ways on two different hemispheres. One side, hotter interior, thinner crust, large and long-lived volcanism, big basalt seas. The other side, cooler interior, thicker crust, limited lava, deep regolith and heavy impact overprint. That is not just a curiosity about our moon. It's a test case for how small planetary bodies can cool asymmetrically in general. Maybe a colossal early impact like a SPA redistributed heat-producing elements and softened one hemisphere more than the other. Maybe radioactive elements like uranium and thorium were never evenly distributed in the first place, concentrating more on the near side and boosting its heat budget. The far side, with its cooler lavas, thick crust, porosity profile, and impact-dominated surface, is the control side in that experiment. So your simple picture of the moon, one uniform grey ball with some darker patches, really is gone at this point. What China's missions are showing is a world that locked in a built-in thermal imbalance, and then kept the evidence on the surface and in the shallow subsurface for billions of years. For planetary science, that turns the moon into a live lab for studying asymmetric cooling, layered crusts, and how giant impacts can permanently rewire a body's interior. And if you accept that, the next step almost forces itself. If the temperature profile, porosity, and chemistry all say cooler, thicker crust with complex buried structures, then you have to ask, what exactly is hiding under that regolith in terms of big shapes, buried basins, and thin lava units? Because once you start mapping those deep structures, you stop seeing the far side as just fluffy soil and start seeing it as a stack of hidden basins and ancient lava rivers locked under hundreds of meters of ejecta. You already know the regolith at von Karman is thick and messy, but the bigger shock is this: the floor you see is not the real floor. Under that 12-meter blanket and the blocky layer below it, the deep radar and orbital data say the terrain itself is warped by structures on the scale of entire basins. What looks like a flat landing site from a distance is actually draped over hidden rings and buried rims from older, larger impacts. When scientists combine LPR profiles with high-resolution topography and gravity maps, they see subtle but consistent hints of ring-like features and long-wavelength bumps and dips under the regolith. Those are what you expect from buried impact basins, where the original crater walls and central structures have been partly filled but not erased. In other words, South Pole Aitken didn't just hit once and call it a day. This region stacked multiple huge basins on top of one another, then later lava and ejecta partly filled and smoothed them. Von Karman's floor is sitting on top of that entire buried landscape. So instead of crater on a slab, you have crater on top of older basins, filled and refilled, all inside one giant outer basin. You're effectively looking at the top layer of a structure that has been hit, thinned, sagged, and refilled many times. That's why the gravity field here is so odd, and why the crust under SPA is so thin compared to the rest of the far side. Then there's the question everybody cares about: how much of what lies beneath is lava, and how much is impact junk? Deep LPR echoes, plus the way gravity varies over the region, point to a structure where relatively thin layers of mare basalts, maybe a few hundred meters thick, sit on top of much thicker packages of impact ejecta. The numbers vary from model to model, but the pattern is the same. Lava is the thin topping, ejecta is the bulk. That's very different from some big near-side Maria, where the story is a thick stack of lava fills an old basin. In those places, Mare basalt can be kilometers thick, miles of solidified lava flooding a structural low. On the far side at von Karman, the signal says something else. Thin basalt flows poured over pre-existing ejecta layers and then got buried and broken up. The architecture is flipped. Lava is not the main component here. It is one layer in a stack dominated by impact debris. This matters because lava and ejecta tell you different things about the moon's interior. Lava records where and when the interior was hot enough to partially melt and send magma to the surface. Ejecta records where and when giant impacts punched deep holes and threw that material across the surface. The fact that ejecta dominates the thickness here is another confirmation that SPA is fundamentally an impact-dominated environment, with volcanism as a secondary modifier rather than the main actor. But even if you never drill down through those hundreds of meters of ejecta and basalt, you are not blind to the chemistry of the buried flows. U22 is constantly driving over fragments that were ripped out of those units and mixed into the regolith. When VNIS sees basaltic clasts along the rover's path, it can read their iron, titanium and magnesium content from their spectra. That effectively gives you samples of buried lava layers without ever cutting a core. Once you have those numbers, you can compare them to what we already know from near-side samples, Apollo basalts, Chang'e 5 basalts and meteorites. Do the far-side basalts have the same titanium content range? Do they come from similarly enriched mantle sources, or from a cooler, more depleted region? Are they older or younger than the bulk of near-side lava flows? Differences in FeO, TiO2 and MgO tell you whether the magma sources were melting at similar temperatures and pressures, and whether they shared the same history of enrichment in certain elements. This cross-comparison is crucial, because it turns random basalt chips at von Karman into a record of how magma sources evolved at different depths and times across the Moon. A small shift in titanium content, or a different ratio of iron to magnesium, can tell you that the mantle source under SPA was cooler, less enriched, or tapped at a different depth than the mantle under, say, Oceanus Procellarum on the near side. With enough data points, you're not just mapping where lava came out, you're mapping how the interior changed over hundreds of millions of years. All of this sits on top of one brutal fact about age. South Pole Aitken is thought to be more than 4.2 billion years old, with some estimates pushing it to around 4.33 billion years. That means SPA formed very early, not long after the Moon itself solidified from its magma ocean. The basin floor, the buried rings, the thin layers that later seeped into its low areas, all of that is recording events from the Moon's first billion years, the era when the crust was forming, thickening and being hit repeatedly by large impactors. When you match the buried structures under von Karman, seen in radar and gravity, to samples with radiometric ages, and to crater counts on the surface, you start reconstructing a timeline. You can say SPA formed around this time, then some hundreds of millions of years later, this smaller basin formed and filled. Then lava of this composition erupted and flowed into that low. Then another impact threw ejecta from this depth into this region. Step by step, you rebuild a sequence of giant impacts and volcanic aftershocks that shape not just SPA, but the entire far side crust. That timeline doesn't just stay on the Moon. The same heavy bombardment hit Earth, but Earth erased most of the evidence. SPA's buried basins and hidden lava rivers become a stand-in for Earth's missing early chapters. If you can read when those basins formed, how thick their ejecta blankets are, and what kind of lava came afterward, you get indirect constraints on how violent Earth's surface was at the same times, how often it was sterilized by big hits, and how fast it recovered. So at this point, the far side is not just a map of craters and a deep rubble blanket. It's a layered record of basins stacked on basins, thin lavas over thick ejecta, and impact ages reaching back to the dawn of crust formation. And once you accept that this stack is that old and that complex, the next hard question comes up. What is all that history doing to the dust itself over billions of years, down to the grain scale? Because the way dust sorts, organizes, and moves on a body like this doesn't just affect science, it directly affects whether your future base or telescope will stay clean, stable, and alive. How can a world with no air, no rain, and no life still have soil that looks like it has been organized over time? On the far side, U22's data show that the dust and small rocks under its wheels are not just a random scatter. There is structure hiding in that grey mess, and it comes from physics, not from any kind of biology. Along the rover's track, high-resolution images and detailed measurements of how the surface reflects light and heat show that grain sadsmores and small clasts follow patterns. When scientists run statistical analyses on the spacing and sizes of these particles, they don't get pure randomness. They see trends, clumps, and alignments that are best explained by the cumulative effect of three main processes: micrometeoroid impacts, seismic shaking from larger impacts, and electrostatic forces acting on the tiniest grains. Micrometeoroids, tiny particles flying through space, hit the surface constantly at several kilometers per second. Each impact is small, but over millions and billions of years they chip away at rocks, create new dust, and move material by kicking it up and letting it fall again. Larger impacts, even from rocks only a few meters across, send shockwaves through the ground and shake nearby slopes. That shaking can cause small particles to roll downslope, settle into gaps, and gradually sort themselves by size and weight. So even without water or wind, you still have a kind of slow mechanical sorting happening over long time spans. Radar scattering, data and thermophysical models add a vertical dimension to that picture. LPR and temperature-based modelling together say that the finest grains dominate the top tens of centimetres, maybe the upper 20 to 50 centimetres, so roughly 8 to 20 inches. Below that, larger clasts, pebbles and small rocks become more common. That gradient is exactly what you expect from what planetary scientists call impact gardening. Over time, micro-impacts shatter rocks and tend to kick the smallest fragments upward more easily than the big ones. Those fine grains either land near the surface or get lofted a bit and resettle. Larger pieces are harder to move and tend to stay slightly deeper, especially if they are buried by ejecta or by the fallout from later impacts. Over meters of depth, the net result is a soil profile where the top is dominated by fine dust and sand-sized material, and the deeper layers carry more of the coarse, blocky content. You can think of it as the moon slowly sorting its own soil column over billions of years. Not perfectly, but in a clear statistical pattern. Then there's the part that feels counterintuitive if you're used to thinking no atmosphere means no dust movement. The far side, just like the near side, is constantly being charged by solar ultraviolet, the solar wind, and, at some points in its orbit, plasma from Earth's magnetotail. Those charged particles and photons knock electrons loose and charge the surface and the dust grains. Under certain conditions, the electric fields that develop near the surface can become strong enough to lift tiny grains, especially those only a few micrometers across. Those grains don't fly like a sandstorm, but they can hop in slow, low arcs, a few centimeters to maybe meters high, then fall back down. Over long time scales, that kind of electrostatic levitation and hopping can redistribute the finest particles, smoothing some areas and causing subtle accumulation in others. You don't need wind. The electric field plays the role of a ghost wind for the very smallest grains, moving them in a way that actually matters over millions of years. Put these effects together, micrometeoroid chipping and lofting, seismic shaking from impacts, and electric charging and levitation, and the self-organization idea makes sense. The dust and clasts are not arranging themselves on purpose, obviously, but the physics pushes the system towards specific patterns in grain size and distribution. You get more fines at the very top, certain alignments along slopes and ridges, and preferred locations where dust tends to gather or be swept clear over time. For pure science, that teaches you how an airless body manages its surface over geological time. But for operations, for humans and hardware, it is a warning. Lunar dust is not just a visual effect, it is an engineering enemy. It is sharp, it is abrasive, and it sticks to surfaces through electrostatic forces. Knowing how it organises and migrates on the far side tells you where the worst trouble spots are going to be. If the top tens of centimetres are dominated by ultrafine grains, those are the ones most likely to get into seals, joints and connectors. They are the particles that will stick to visors, cover solar panels and wear down moving parts. If those grains tend to move downslope, craters, pits and low-lying areas might collect thicker dust layers over time. If electrostatic hopping tends to smear dust across ridges or high points at certain times of the lunar day, that affects where you place antennas, mirrors or exposed optics. The farside data say the moon is constantly slowly sorting and reshaping its dust carpet. You're not dealing with a static dead coating. You're dealing with a surface that reacts to every new impact, every seismic jolt, every sunrise and sunset in subtle but cumulative ways. For planning a radio observatory on the far side, that matters. Long cables and dipole antennas laid out over the regolith will have to survive dust settling and moving on timescales of years to decades. For a future human base, it matters even more. Airlocks, rover garages, and habitat inlets will sit in an environment where fine dust is always one nudge away from moving again. So this self-organisation story is not just a curiosity about patterns and grain size, it is a design constraint. It tells you that you cannot treat dust as a uniform layer that behaves the same everywhere. You have to map where it is likely to accumulate, where it will be relatively thin, and how it will respond to the electric environment your own systems create. A large base or power station will change local charging conditions, potentially altering dust motion right around your hardware. By now you can see the theme. Every time you look more closely at the far side, the picture gets more structured, more dynamic, and more demanding. Even the dust has a long, complicated history and clear behaviour rules. And that leads directly to a bigger question about survival and opportunity. Because while the far side's dust is trying to infiltrate everything you build, the radiation environment above it and the radio silence around it are opening up one of the best locations in the solar system for listening to the universe itself. On the far side of the moon, the thing that threatens you most is something you never see or hear. Radiation that just keeps coming all the time from every direction. The moon has no global magnetic field, no thick atmosphere, nothing like Earth's shield. So galactic cosmic rays and solar particles hit the surface directly. Measurements from lander instruments and comparison with radiation models YES show that the dose rate at the surface is hundreds of times higher than what you get on the ground on Earth, especially during solar minimum when the sun's magnetic field is weaker and more deep space particles get through. You are basically standing in a slow, constant particle storm. That has two hard consequences. First, long-term unshielded human presence on the surface is not realistic. You'd push past safe lifetime dose limits in a relatively short time compared with an Earth career. Second, even electronics and materials age faster, because high-energy particles damage components, flip bits in memory, and create defects in semiconductors. That's why every lander and rover has to be built like a radiation test article by default, and why far-side bases cannot simply sit on the surface without protection and hope for the best. So the same regolith that chews up hardware with dust suddenly becomes one of your best tools for survival. On the far side, you're sitting on roughly 12 meters of rubble, about 40 feet. If you dig down just 2 to 3 meters, say 6 to 10 feet, and pile that much material on top of a habitat, the mass above you starts acting like a serious shield. Those meters of soil translate into metric tons of rock per square meter, enough to absorb and scatter a large fraction of incoming cosmic rays and solar energetic particles. Models and analog studies suggest that with a couple of meters of cover, you can drive radiation doses down toward the range astronauts see on the International Space Station, or even below, depending on the exact composition and density. That doesn't make the far side safe in the way Earth's surface is safe, but it does make long-term habitation technically plausible using local material, not imported steel or water tanks. The same 12-meter profile that records billions of years of impacts also gives you the raw mass you need to stay alive in that particle field. Radiation is the invisible threat. But the far side's biggest advantage, the thing no other place near Earth can offer, is also invisible: silence. Not quiet in the sense of sound, there's no air for sound anyway, but quiet in radio. The entire bulk of the moon sits between you and Earth. That blocks almost all of Earth's radio noise, everything from FM music stations, to radar, to satellite downlinks, to random interference from our entire civilization. Near Earth, everywhere else in cislunar space, that noise is unavoidable. On the far side, it just doesn't reach you. Combine that with the tall walls of the South Pole Aitken basin, and craters like von Kármán become natural bowls where low-frequency radio waves from the rest of the universe can reach you, while signals from Earth are blocked or strongly suppressed. There is no other place this close to home that gives you a radio-quiet zone of that quality. That is exactly what low-frequency radio astronomers have been dreaming about for decades. The frequencies below about 30 MHz are mostly lost from the ground, not because they don't exist, but because Earth's ionosphere blocks or distorts them. You simply cannot build a ground-based telescope to listen to those bands properly. From orbit around Earth, you still fight Earth's own radio noise. From the far side, that noise is gone. So if you lay out long dipole antennas and simple radio receivers across the regolith in a far-side crater, you suddenly have access to a part of the spectrum that no ground observatory can touch. That opens a direct path to one of the hardest questions in cosmology. What did the universe look like before the first stars and galaxies turned on, during the so-called Dark Ages? Hydrogen atoms in that early era emit and absorb radio waves at a wavelength of 21 centimeters, which gets stretched to longer wavelengths as the universe expands. By the time that signal reaches us today, it sits down in those low-frequency bands that Earth blocks. A far-side array, listening below 30 MHz, could pick up the global glow and faint fluctuations from that hydrogen, telling you when the first stars formed, how fast they heated and ionized their surroundings, and how structure grew in the very early universe. Chang'e 4 quietly proved the prerequisite steps for that kind of project. It showed that you can land hardware on the far side, power it through those insane temperature swings, communicate reliably through a relay satellite at the Earth-Moon L2 point, and operate instruments for years in that radio-quiet environment. You now know you can get a rover and a lander to survive out there, and you know how to bounce data back to Earth without breaking the radio silence at the surface. That means the technical barrier to a low-frequency far-side radio array is no longer, is it even possible? It's, who will commit to build it and how big will they go? The site around von Kármán, with known regolith thickness, mapped boulder fields, and proven relay operations, is a prime candidate. You could start with a small pathfinder array, then scale up to kilometers of antennas spread inside SPA's vast interior. So the far side is a paradox in your planning. At ground level, radiation and dust are trying to wreck your hardware and hurt your crew. A few meters down, that same regolith becomes your radiation shield. Above you, the sky is full of dangerous high-energy particles, but in radio it is quieter than any place you can find near Earth. And that silence is exactly what you need to listen to the faintest signals from the early universe. And that tension doesn't end with radiation and radio. The next hard limit for a far-side base or observatory is even more basic: water. Because once you've figured out how to shield people, protect hardware, and use the silence, you still have to ask a brutal question. Is there enough water on this side of the moon to support anything long-term? Or are you trying to build in one of the driest accessible places in the solar system? You keep hearing that the moon has water, so the natural assumption is, great, just land, scoop, melt, and you're done. The problem is, when you look closely at the far side, especially in South Pole Aitken, the story shifts from the moon has water to this part of the moon might be almost bone dry compared to what you were hoping for. First, how did we even get the idea that there's water or hydroxyl out there in the first place? Long before Chang'e 4 and Chang'e 6, orbital infrared data from missions like Chandrayaan-1 and NASA's Lunar Reconnaissance Orbiter showed weak absorption features consistent with hydroxyl, OH, and possibly molecular water bound in minerals or stuck on grain surfaces. Those detections showed up on both near and far sides, especially at higher latitudes and in the cooler parts of the day. But there's a catch. Those orbital measurements are indirect. Each pixel covers kilometers of terrain, averages over many rock types, and sees just the top millimeter or so of surface. You can't tell if you're looking at a thin coating on grains, trace water in volcanic glass, or something else. You just know that some hydrogen-bearing species are present in tiny amounts smeared out over large areas. That's enough to say there is some water signal, but not enough to plan a mine. Ground truth had to come from actual samples, and that's where Chang'e 6 hits hard. It returned the first ever far-side samples, about 5 grams of soil from the Apollo Basin area inside SPA, not too far geologically speaking from where Chang'e 4 operates. Detailed lab work on 578 individual particles from that soil showed water contents under about 1.5 micrograms per gram. That is extremely low. On the near side, in some samples, water contents in grains range from roughly 1 to 200 micrograms per gram. So in some cases, The far-side grains in this region have up to 100 times less water than their near-side cousins. That is a major reality check. Yes, there is water at the grain level, but in this part of the far side, it is at trace levels, way below what near-side volcanic glasses or certain pyroclastic deposits can offer. You're not looking at rich hydrated layers, you're looking at almost dry rock with tiny amounts of water bound in it. Now, what can U22 add to that, given that it doesn't carry the same kind of water-dedicated sensors? It still contributes indirectly. From U22's perspective, the regolith composition and the way the soil handles heat both point to a mix that is drier and more refractory, meaning it resists melting and doesn't carry a lot of volatile material. The spectra show less of the glassy volcanic ash that on the near side can be rich in hydroxyl, and more of the older northocite and deeply excavated crustal material. The thermal behaviour you saw earlier, with low but not ultra-low thermal inertia and no strong signs of volatile-rich layers near the surface, fits that picture. If you had widespread hydrated glass or ice mixed in, you'd expect different signatures as it sublimates or changes phase. Instead, everything points toward a surface dominated by dry, hard minerals that have survived multiple heating cycles without losing much water because there was not much to lose. Together, the in-situ data from Chang'e 4 and the lab results from Chang'e 6 push toward the same conclusion. At least in SPA's basaltic plains, the far side may be intrinsically drier. For resource planning, that conclusion hits directly where it hurts. If you're thinking about mining water for rocket fuel, life support, or radiation shielding, these numbers say that the SPA interior is not your best hunting ground. The grains simply don't hold enough water to make baking the soil a practical primary source. On the near side, certain volcanic deposits and some regions with hydrated glass might give you interesting yields. At the poles, both near and far side, permanently shadowed craters likely trap real ice, mixed into the soil, delivered by comets and other sources. So if you're a mission planner, the Chang'e 6 result quietly changes your map. For bulk water, you look toward near-side polar cold traps, or specific pyroclastic deposits, where volcanic glass beads hold more hydroxyl, not mainly toward SPA's interior plains. The far side, especially in the region we're talking about, starts to look like an excellent place for geology, radio astronomy, and long-term science infrastructure, but not a place where water comes free with the dirt. Does that kill the idea of a far side base? No, but it changes the logistics. A far-side outpost in or near SPA will probably need one of three strategies, or some combination. 1. Haul water in from elsewhere, including from near-side resource hubs or from Earth in the early stages. 2. Tap polar ice, potentially with a supply chain running from a South Polar mining operation to a far-side science base. 3. Push recycling hardware to the limit, closing the loop on every drop of water used for crew, cooling, and industrial processes. It also raises another sharp question. Why is this region so dry compared to some near-side sites that have much higher water content in their grains? Is it simply that different types of volcanic activity happened here, with less water in the magma? Is it that impacts in SPA, with their enormous energies, are better at stripping volatiles away? Or is it tied back to the deeper asymmetry you've seen already, the far side's cooler interior, thicker crust and lower abundance of heat-producing, volatile-related elements? Those questions push you straight into the big picture, because at this point you're not just stacking details, you're staring at a global split. One hemisphere with thinner crust, hotter mantle, richer volcanism, more hydrated glasses in some places, and big creep-rich regions. The other hemisphere with thicker crust, cooler interior, fewer mare seas, drier soils in SPA, and a different balance of heavy elements. So the water story is not just a logistics headache, it's another piece of evidence that the moon has two faces in a fundamental way. And that sets up the next step, where you stop treating these differences as the list of odd facts and start asking the core question: why did the moon end up with this great asymmetry at all, and what happened early on that locked in two separate thermal and chemical histories for the same body? You're looking at one moon, but the more data you stack, the more it behaves like two different worlds glued back to back. At this point you've seen differences in soil, chemistry, heat and water. Now it's time to put that together and ask directly, why does one face of the moon look and behave so differently from the other? Start with the simplest, hardest numbers: crust thickness and composition. Gravity and topography data show that on average, the far side crust is thicker. A common estimate is something like 50 to 60 kilometers thick, roughly 30 to 37 miles, over large regions. The near side, especially under the big maria and basins, is noticeably thinner, often closer to 30 kilometers, about 19 miles. That difference alone explains a lot. A thinner crust is easier to crack and tap with magma. A thicker crust is harder to break and flood with lava. South Pole Aitken is the exception carved right into that rule. Under the floor of SPA, the crust is thin to maybe about 30 kilometers or less, while the surrounding far side highlands jump back up to the thicker values. Von Karman sits inside that thinned zone. So the rover is sampling crust that was already excavated and stretched once by the SPA impact before later craters and limited lava fills added their layers. It's like doing geology in a place where the crust has already been peeled back once, then patched over. Now layer in the chemistry of heat. Not all rock holds the same built-in heater power. Certain elements like potassium K, rare earth elements REE, and phosphorus P, often tagged together as KREEP, tend to cluster with radioactive elements like uranium and thorium. When those radioactive elements decay, they release heat inside the crust and mantle. Regions rich in creep can stay hotter for longer and feed extended volcanic activity. On the near side, there's a big well-known anomaly called the Procellarum creep terrain. It is enriched in K, R, E, E, P, U, and TH compared to much of the rest of the moon. That's where you see some of the thickest mare basalts and long-lived volcanic activity. SPA and much of the far side do not show the same levels of enrichment. Orbital gamma-ray and neutron data, plus sample work, say the far side, especially inside SPA, is poorer in these heat-producing elements. That lines up with what you've already seen. Fewer large mare seas, cooler lavas, thicker crust that did not get repeatedly flooded. So right away, you have a lopsided mantle and crust in terms of both thickness and internal heating. One side thinner and richer in natural radioactive fuel, the other thicker and poorer. The big question is, how did that happen on one small body that formed from the same initial impact and magma ocean? One leading idea is that the SPA impact itself rewired the interior. Recent models and analyses of SPA-related material suggest that when a gigantic impact, maybe with an impactor around 200 kilometers wide, slammed into the proto-moon at tens of kilometers per second, it did more than just dig a big hole. It would have dumped enormous energy into the crust and upper mantle, partially liquefying them in that hemisphere. In that scenario, dense melts enriched in radioactive elements and iron-bearing components could have flowed or been pushed away from the impact site over time, concentrating more of the creep-rich material on the opposite hemisphere, the side we now see as the near side. So the far side, especially inside SPA, ends up thinned and depleted in heat producers, while the near side gets a thicker layer of hotter, radioactive-rich material that keeps feeding volcanism later. You basically get an internal mass shuffle triggered by one colossal event 4.2 to 4.3 billion years ago. That picture fits several things at once: a cooler far side interior, fewer mare basalts there, a creep-heavy near side, and a large, deep basin on the far side that matches the energy needed for such a reorganization. It's not proven in every detail, but it is a coherent way to connect crust thickness, chemistry, and volcanic history. There is another, more radical idea: the two-moon hypothesis. In that story, the early Earth-Moon system didn't just have one moon for a while, it had two. A smaller companion moon, maybe a few hundred kilometers across, would have occupied a nearby orbit and over time spiraled in and merged gently with the larger moon. Instead of a catastrophic high-speed smash, you get a slower, more controlled collision, where one hemisphere of the main moon gets plastered with extra crustal material. In that model, the far side highlands are basically the remains of that smaller sibling forming a thicker, compositionally distinct cap. The near side would keep more of the original magma ocean crust and creep-rich mantle upwellings, giving it a different thickness and chemistry pattern from the plastered side. The two-moon idea tries to explain why the far side looks like an extra thick, heavily cratered shell, while the near side is thinner, hotter, and more volcanic. The problem and the strength of both these ideas is that they now have to line up with a lot more detailed evidence than before. You can't just match broad shapes and say, that looks right. U22's possible mantle-like rocks on the von Kármán floor tell you something specific about what deep material looks like under SPA. Chang'e 6's cooler far-side lavas tell you something specific about crystallization temperatures, iron content and volatile levels there. Gravity and topography constrain the actual crust thickness to map. Any model, SPA rewiring or two-moon merger, has to hit those targets. It has to reproduce a thick far-side crust except under SPA, a creep-rich near side, a cooler far-side mantle, specific olivine and basalt chemistries in SPA, and the long-term volcanic asymmetry. That's a high bar, and that's exactly why these new Chinese missions are so disruptive. They turn arm-waving maybe scenarios into hard tests with real numbers. What you can say with confidence already is this: the old mental model of the moon as a mostly homogeneous grey ball with random dark stains is done. What China found by going to the far side is that the moon is more like a hemispheric experiment in planetary physics. One face, thin crust, hot interior patches, enriched heat producers, broad Maria. The other face, thick crust, depleted in radioactive fuel, cooler interior, fewer and thinner lavas, deeper regolith, and a record of massive impacts stacked on top of each other. Those two faces are linked by one of the largest impact basins in the solar system, South Pole Aitken, and maybe, depending on which model ends up winning, by a vanished second moon that merged away early on. Either way, the symmetry is broken, and it stayed broken for over 4 billion years. Once you accept that, one last question becomes impossible to avoid. If the moon spent its entire early life recording big impacts, volcanic aftershocks, and interior cooling in this asymmetric way, what can that record tell you about Earth's own missing past? Because our planet was in the firing line too, but it erased almost all of that history. The moon did not, and that turns it into something much bigger than a pretty object in the sky. It turns it into Earth's missing history book. When you look at the moon now, you're not just looking at a neighbour, you're looking at the evidence locker for Earth's missing childhood. Earth's surface has been wiped and rewritten over and over by plate tectonics, mountain building, erosion, oceans, life, everything. Old craters get subducted, buried, or worn away. The moon has none of that. No plates, no rain, no oceans. So its highlands and big basins, especially on the far side, still carry the scars of the same late, heavy bombardment. And earlier impact epochs that Earth went through but erased. South Pole Aitken is the biggest chapter in that record. It's roughly 2,500 kilometres across, about 1,550 miles and up to 13 kilometres deep, around 8 miles. That is not just another crater, it's a basin, on the scale of a small hemisphere, carved early in lunar history. Every layer of ejecta in and around SPA, every buried basin inside it, is a record of impact conditions when the inner solar system was still full of large projectiles. When you study SPA, you're indirectly studying what was hitting Earth at the same time. To turn that from a story into a timeline, you need ages, not just shapes. This is where returned samples matter. From the near side, Apollo and Chang'e 5 gave us radiometric ages for major mare basalts and basin ejecta. From the far side, Chang'e 6 adds the first age anchors inside SPA. Once you know, for example, that SPA formed around 4.3 billion years ago, and a smaller nearby basin formed around 4.1 billion years ago, you can go back to orbital images and simply count craters on their surfaces and ejecta blankets. The logic is straightforward. Older surfaces collect more craters. If a surface with a certain crater density dates to 4.3 billion years, and another with a slightly lower density dates to 4.1 billion, you can start building a curve, crater density versus absolute age. Then for regions where you don't have samples yet, you can read crater densities like ticks on a calendar and assign reasonable age ranges. That is how the Moon's surface gradually turns into a time axis, and that same calibration is then used carefully on other airless bodies like Mercury and Mars's older planes. The Moon's story is also crucial for something deeper, how magma oceans cool and freeze on rocky worlds. The standard picture is that the young Moon was mostly molten after the giant impact that formed it. Over time, lighter minerals floated up to build the crust and denser ones sank to become the mantle, and leftover melts with odd compositions pooled in between. The key point is, the Moon's global magma ocean froze relatively quickly, compared to Earth's deep convecting mantle, which stayed mobile for billions of years. By studying the far side in detail, you get constraints on that cooling process. Mantle-like rocks in von Kármán, the composition of buried basalts in SPA, and the cooler crystallization temperatures recorded in Chang'e 6's far side lavas all tell you how the Moon's interior separated and lost heat. If you know, for instance, that certain olivine-rich rocks must have formed under specific temperature and pressure conditions, you can back out how thick the early lunar crust was, how hot the mantle was, and how fast it cooled. Once you can do that for the Moon, you can start scaling the physics to other worlds, early Earth, Mars, even rocky exoplanets. Earth's magma ocean would have taken longer to cool because Earth is bigger and holds heat better, but the basic processes, like minerals rising, heavy ones sinking, heat-producing elements concentrating in certain layers, are the same. The Moon becomes a stripped-down, easier-to-read version of the same story, without plate tectonics constantly scrambling the evidence. Then there's the question of what impacts did to volatiles, things like water and carbon. Impact melts and tiny glass beads on the Moon don't just record the target rock, they also preserve information about the impactors themselves. From their chemistry and structure, you can estimate impact velocities, often 10 to 20 kilometers per second, 6 to 12 miles per second, and total energies. Those numbers matter because at some speeds and angles, impacts are good at delivering volatiles by bringing in cometry or icy material and letting part of it stick. At higher speeds, or in certain conditions, they can do the opposite. They can heat and blow off existing volatiles from the surface and even from shallow crustal layers. The drier soils in SPA, especially compared to some near-side regions with hydrated glasses, hint that at least here, the combination of impacts and local conditions tended to strip or fail to retain water, rather than enrich the surface in it. That's important for two reasons. First, it shapes how you think Earth got its oceans and atmosphere. If high-energy impacts on a body with Earth's gravity and escape velocity behave differently from impacts on the Moon, you need to quantify that. Second, it gives you rules for other planets and moons. On a small world with low gravity like the Moon, intense bombardment in a region like SPA may be net destructive for volatiles. On a larger world, more of the impactor's water might stick. So when you read the Moon's impact melts, glass beads and basin ages, you're not just filling in lunar history. You're getting practical limits on how often big impacts hit, how violent they were, how long magma oceans stayed liquid, and how efficiently they delivered or removed water and carbon. All of that feeds into one central question: under what conditions does a young rocky planet calm down enough and hold on to enough volatiles to become a place where long-term oceans and eventually life can survive? By now, you can see why the far side is not just a cool destination. It's a tool for reconstructing Earth's own lost timeline. Every crater age in SPA, every deep rock U22 analyzes, and every dry grain from Chang'e 6 puts another constraint on how violent Earth's early environment really was, and when it transitioned from hellish bombardment to something stable enough for biology to take hold. And once you realise that, the stakes on what happens next go up. Because now the question is not only, what did China find on the far side, it's, what are we going to do with that knowledge? Do we build bases, telescopes, and mining operations that exploit this laboratory without destroying it? Or do we treat SPA like just another resource pit? The next step is about decisions, not just data, where bases go, how radio arrays are built, and how we balance science against extraction on the moon's hidden face. Right now, you're living in the middle of a shift where the far side stops being just a mystery and starts becoming a planned workspace. China isn't treating Chang'e 4 as a one-off stunt. It's one link in a chain. Chang'e 4 showed you can land on the far side, survive those heat swings, and talk to Earth through a relay at Earth-Moon L2. Chang'e 6 took the next step, went into SPA, grabbed actual soil, and brought it home. On the roadmap, Chang'e 7 and Chang'e 8 target the South Polar region, aiming at permanently shadowed craters and potential ice, with the stated goal of building toward a joint research station on the moon. Why does that matter for the far side? Because once you know how to do polar landings and resource scouting, and you already know how to run a far side relay mission, you can link the two. You can picture a network where polar missions supply water and volatiles, while far side SPA missions supply deep geology and radio astronomy. The dark side stops being a disconnected target and becomes one node in a larger, coordinated system of bases and relays. So where would you actually put a serious far-side base if you had to choose a spot today? You'd want three things at once: good engineering conditions, high science value, and a way to feed the base with power and resources. Engineering-wise, you want relatively flat terrain, not on top of a sharp crater rim or inside a steep-walled pit. Parts of von Kármán's floor near the Chang'e 4 landing area already fit that bill. We know the regolith thickness there is about 12 meters, roughly 40 feet. We know the density profile, we know it's cluttered with decimeter to meter scale rocks, and we know the mechanical behavior at least in one small zone. That reduces risk. Scientifically, you want to stay within SPA, or right on its edge, because that's where the deep excavated material is. A base near von Karman gives you access to far-side highlands, SPA basins, and any future drill cores set up to tap those stacked ejecta and lava layers hundreds of meters down. If you put people and more capable rovers there, you can systematically map and sample the deep crust and possible mantle material that U-22 only scratched at. Logistically, you'd prefer a location that can tie into polar infrastructure, or at least work well with relay satellites. That means you either pick a site that has line of sight to a polar relay network, or you invest in a more complex web of L2 and polar orbit relays. Either way, you're not dropping a random outpost, you're building a node at a place already tested by Chang'e 4, with known dust behavior, known boulder fields, and proven comms geometry. Once you have people and power on the far side, the next obvious target is not underground, it's up in the sky, or more precisely, in the radio spectrum. SPA is a roughly 2,500 kilometer wide bowl, about 1,550 miles, and its interior is shielded by the basin walls and the moon itself from Earth's radio noise. If you want a place to build a low-frequency radio observatory, this is about as good as physics is going to give you in near-Earth space. Technically, the hardware you need is not exotic. Low-frequency radio telescopes can be built from long, thin dipole antennas, metal wires or tapes a few to tens of meters long laid directly on the regolith or slightly elevated. You can roll them out from rovers or small robots like tape measures, connect them to simple receivers, and link them back to a central station. Spread that over kilometers and you have an array. Spread it over tens of kilometers and you have a facility that can map faint signals from the early universe in detail no current system can touch. With the far side's radio silence, you can finally access frequencies below about 30 MHz without Earth's ionosphere blocking, distorting or drowning them in human-made noise. That's the band where the red-shifted 21cm hydrogen signal from the cosmic dark ages lives. A far-side array in SPA could track how the neutral hydrogen around the first stars heated and ionized, how early structures grew, and how the universe transitioned from dark to lit. That's not just another telescope, it's a completely new window, one that literally cannot open from Earth's surface. At the same time, you can't pretend the far side is just a science park with no resource angle. Even if SPA soils look dry in terms of water, they are rich in metals and oxygen-bearing minerals. Ilmenite, an iron titanium oxide FeTiO3, shows up in many basaltic components. You can process it to extract oxygen, leaving behind iron and titanium. Silicate minerals, which dominate the crust, can be smelted or sintered into structural material, bricks or glass. For construction, radiation shielding and oxygen production, the raw ingredients are there in vast quantities, measured in billions of tons. But here comes the tension. The same regolith and rocks that you want to mine are also irreplaceable scientific records. SPA's stratigraphy, the precise layering of ejecta, basins and thin lavas, is a once-only archive. Bulldozing large areas, digging massive open pits, or heavily disturbing certain key sites could permanently destroy evidence about early impacts, interior structure, and volatile history that you can't reconstruct later. This is where the detailed work of Yutu-2 and the lab results from Chang'e 6 become more than nice papers. They are the baseline maps you'll use to decide what must be protected. If radar profiles say a certain area holds a clean, readable stack of ejecta from multiple known basins, or if chemistry says a particular outcrop is likely to be mantle-derived, that region becomes a candidate for a protected science zone. If other regions show more homogeneous basalt rubble or heavily reworked regolith with less unique information, they become better candidates for targeted resource extraction. So you're heading into a future where the far side is pulled in two directions, a laboratory for deep time and interior physics, and a resource field with oxygen, metals, and usable regolith. Managing that balance is going to be messy, and it will depend on how seriously spacefaring nations take long-term scientific value versus short-term utility. There's one core message you can't skip. When you say what China found on the moon's dark side, you're not talking about a single gel-like patch or one weird olivine-rich boulder. You're talking about a complete overhaul of how we see the moon. The far side forced you to accept that the moon has two different crusts, two different heat budgets, two different volcanic histories, and two different water stories all locked into one body. Chang'e 4 and Yutu-2 showed that the regolith is deep, structured, and older than anything Apollo walked on, that the subsurface is full of stacked ejecta and thin lava layers, that there are rocks on the surface that might come from the deep interior, and that flashy anomalies like the gel are really bits of extremely violent impact history. Chang'e 6 then confirmed that SPA soil is drier and that farside lavas cooled cooler, backing up the idea of a cooler, less enriched interior. Put bluntly, the far side is no longer just the hidden face of the moon. It's the key to why the moon looks the way it does, why Earth's early bombardment history looks the way it does, and why small rocky worlds can freeze into asymmetric, two-faced states that last for billions of years. When you show your audience that, you're not just giving them a tour of some distant crater, you're walking them through the process of watching a simple moon fall apart and reassemble as a complex, split personality world that still holds the missing pages of Earth's own story. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.